Okay, chapter 3. I have uploaded notes on chapter 3 in Microsoft Teams. Chapter 3 is on AC meter. Chapter 2 DC meter. Chapter 3 AC meter. These are the outcome of the learning for this chapter. Number 1 is to list 5 principal meter movements and application for each. Number 2, to describe the purpose and operation of the diode in half-wave rectifier circuit and full-wave rectifier. Number 3, describe the purpose of the second diode in a half-wave rectifier, which is often used in rectifier circuits. Number 4, lists 5 applications for electrodynamic movement. And the last one is to list the typical frequency range of the ion vein meter movement. Okay. Okay, so these are the subtopic in this chapter. Introduction, and then the observer meter movement with half-wave rectifier, followed by full-wave rectifier, AC voltmeter and other AC meter movement. Okay. AC signal. AC is an electrical current whose magnitude and direction vary sinusoidally with time because for each instantaneous time, the signal vary with time. Okay. At 0, when time is 0, so let's say for this signal voltage here, at time equal to 0, so voltage is equal to 0. At time is half, the voltage is equal to 0. At full time of period, the voltage is equal to 0. 0 as well. Please mute your audio. Charlene. Okay. Class can see my screen?
Can.
Okay, so the voltage is at peak when T is equal to T over 4 here. Okay, so that's why we say that magnitude and direction vary sinusoidally with time. Compared with DC signal, the signal is fixed for the signal is fixed. Okay. Current reverses at regular time intervals and has alternately positive and negative value. Okay, positive and negative value. The sinusoidal waveform, sine wave, for example, so sinusoidal is sine wave, is the fundamental of AC current and AC voltage waveform. The RMS value is the effective value of a varying voltage or current. It is equal with steady DC value which give the same effect. VRMS is equal to VP over Z2, or VP is equal to VRMS Z2. The average voltage or current of an AC signal is 0 because the positive and negative parts exactly cancel out. Okay, so this is a sine wave. This is peak voltage. It is from 0 to the peak. Peak to peak value is from the peak to the peak. Let's say the peak value here is 5 volts. So peak to peak voltage is equal to what?
10.
10. Okay, so RMS is V peak over Z2. It is about 1 over Z2 is 0.7, right? 0.707. 0.707 meaning that about 71% of the peak value. So RMS is about here, about 71% of the peak value. What do AC meters show? Is it the RMS or peak voltage? AC voltmeters and ammeters show the RMS value of the voltage and current. DC meters also show the RMS value when connected to very DC, providing the DC is varying quickly. For example, a lamp connected to a 6 volt RMS AC supply will light with the same brightness when connected to a steady 6 volt DC supply. However, the lamp will be dimmer if connected to a 6 volt peak AC supply because the RMS value of this is only 4.2. It is equivalent to a steady 4.2 volt DC. Okay, so how to get 4.2 here? How to get 4.2?
Divide by 6.
Okay, 6 divided by 2. If the peak value is meant, it should be clearly stated. Otherwise, assume it is the RMS value. Okay, so usually when we deal with AC signal, so we just assume that the given signal is in RMS. Otherwise, it is clearly stated that the value of signal is in peak value or maximum value. In everyday use, AC voltages and currents are always given as RMS values because this allows a sensible comparison to be made with steady DC voltages and currents such as from a battery. For example, a 6 volt AC supply means 6 volt RMS and the peak voltage is 8.6. Okay, so usually the AC signal is in RMS value. Okay, so these are 5 meter AC meter movements: electrodynamometer, iron weight, electrostatic, thermocouple, and PMMC. So number 1 answer number 4 will be explained at the end of the chapter. Okay, but this is the summary. Electrodynamometer, you can watch the video to know more about the meter movement. Electrodynamometer for standard meter, transfer instrument, wattmeter, frequency meter, iron vein, indicator applications such as in automobiles, electrostatic, measurement of high voltage when very little current can be supplied by the circuit be measured, thermocouple, measurement of radio frequency signal, PMC is most widely used, meter movement for measuring direct current or voltage and resistance. So bear in your mind that PMC is for DC. But now we learn about AC meter. So after this, we will learn how PMMC is converted to design AC meter. Okay, so these are 5 meter movement, 5 type of meter movement. So all the meters can be used for DC signal as well as AC signal, but for PMMC or the ensemble, to measure AC signal, it must be added with rectifiers. Okay, yes, with rectifiers. So these are the application for each meter movement. Electrostatic fluid meter, this is thermocouple, this is field indicators. Okay. In this chapter, the same diaxial meter movement will be used to measure alternating current and voltage. Okay, so the same PMMC that we learned in previous chapter will be used here to measure AC signal. Even though it cannot directly measure alternating current with the ensemble, rectification of the alternating current by using diode rectifier to produce unidirectional current flow will be discussed. So we will add rectification to the PMMC so that it can be converted into AC meter. Rectifier converts AC to DC. Okay, because rectifier, the role of rectifier is to convert AC signal to DC signal, and then using a meter responsive to DC to indicate the value of rectified AC. So we add rectifier into PMMC so that the meter can read AC signal. This method is very attractive since PMMC instruments have a higher sensitivity than the electrodynamometer or the moving iron instruments. Okay. This is supply from TMB, AC sine wave, 240 or 230 V RMS. Okay, AC signal with 50 Hz. This is single phase. Okay, so AC to DC conversion halfway. So this is half wave rectifier. After this, we will learn full wave rectifier circuit. Be added to PMMC to convert the meter so that the meter can read AC signal. So this is input, this is AC signal. We add rectifier circuit. This is rectifier circuit. Rectifier circuit for half wave means that we add a diode. Okay, so in half wave rectifier circuit, we rectify the positive cycle. So negative cycle will be no signal for negative cycle, only positive cycle. This is positive cycle, this is negative cycle. Okay, so we know that VRMS is equal to VP over Z2. Okay, so the PMMC or is a DC meter. It reads a DC signal or average signal. Okay, so V average or VDC or output voltage of the meter is equal to V peak over pi. Okay, or is equal to 0.318 V peak. Vm is same as V peak. So 1 over pi is equal to
0.318.
Okay, so here 1 over pi is here, Vm is equal to V peak here. Okay, so I out is equal to V over R. We take this V out, divided with R. Okay, so we still in half-wave rectifier part. DC voltmeter is modified to measure AC voltage by adding a diode into the circuit. Okay, so this is for half-wave rectifier. We add a diode to the circuit. This is PMMC. Okay, and then it will becomes DC voltmeter to measure AC voltage. The input signal is AC. The meter known as the several meter movement with half-wave rectifier. Type of diode such that can be used, copper, vacuum, and so on. It produces an approximate half sine wave across the load resistor. Half sine wave. Okay, so the average value of the circuit is referred to as the DC voltage. So PMMC reads only DC signal. We call it as DC voltage as well. Average value. We add RS here to limit the current drawn by PMMC. If the current exceeds the current rating of PMMC, then it destroys the instrument. The sensitivity for this meter is equal to, this is the typical formula for sensitivity, 1 over current. Okay, IFST is the current that flows through the circuit. Okay. This is an example. AC voltmeter using half-wave rectifier. This is AC voltmeter. Okay, the whole circuit is AC voltmeter, where this is PMMC DC. Okay, we learned in chapter 2, PMMC measure DC signal, but if we add rectifier, okay, let's say this is half a rectifier, we add a diode to the PMMC circuit and RS, okay, then it can read AC signal. From this figure, sensitivity, okay, SDC. This formula is for DC sensitivity. SDC is equal to 1 over IFSD, equal to 1 over 1 milli. So SDC or sensitivity for DC meter is equal to 1 kilo ohm. 1 kilo ohm per volt, sorry. 1 kilo ohm per volt. Assume that a multiplier of 10 times this value means a 10 VDC input will cause exactly full scale deflection. Okay, so imagine that this PMMC, the voltage range for this PMMC is 10 volt. Okay, 10 volt. How to calculate 10 volt? So V range is equal to R total divided with S. Okay, R total is 10K RS plus 100 here divided with 1K ohm per volt. Okay. Okay, class. Actually, no need to put unit during your calculation. No need to put. No need to put the unit. Okay, just put the unit for your final answer. Okay, so the voltage range for this DC. Okay, let's say this is DC. DC what? DC meter. Okay, DC meter. So V range is equal to this formula, and we get V range is equal to about 10 volts. Okay, so for full scale deflection, for full scale range, so V is equal to 10 VDC. If this DC input is replaced by a 10 VRMS, okay, now let's say the signal is in AC, okay, so now we replace 10 the DC signal to RMS or AC, so it becomes 10 VRMS sine wave input. The voltage across the meter movement is just the positive half cycle of the sine wave due to rectifying action. Okay, so the output will be only positive half cycle because of rectification. Okay, so V peak is equal to SERT2 VRMS. SERT2 multiply with RMS value of the voltage, it is 10. So it is equal to 14.14 volts. The DC will respond to the average value of the AC input. Okay, now this signal is AC, but our PMMC only respond to DC signal or average signal. So we have to find average value. V average is equal to V peak over pi. 14.14 divided with pi equal to 4.5 volt. So now with 10 VRMS or 10 volt AC, the meter read 4.5 volts. Okay, if we convert this average to RMS value, V average is equal to 0. This is the general formula. V average is equal to 0.318 Vm. Okay. Vm is equal to set to Vrms. So V average is equal to 0.45 Vrms. Okay, meaning that with AC signal of 10 volts Vrms, okay, the average value, okay, or the measurement is equal to 0.45 Vrms. So Vrms here is equal to 10. 0.45 multiplied with 10 is equal to 4.5. Okay, 4.5. So with 10 Vrms, the meter reads only 4.5. It is not the full scale of the meter. So DC voltmeter with voltage range is equal to 10 volt. Okay. So now based on previous example, DC voltmeter with V range is equal to 10 volt. With 10 Vrms, the meter indicate only 4.5 volts. Okay. 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 Now, if the DC signal is okay, now the voltmeter is in DC. If the input or if the signal is in DC, so the full range is 10 volt DC as well. But if the signal is in AC, 10 Vrms will indicate only 4.5 volt on the meter. So 10 Vrms voltage, okay, is equal to 4.5 VDC, or 10 VAC is equal to 4.5 VDC for full scale deflection. Okay. Pointer will deflect to 45% only of full scale. A voltmeter is not as sensitive as the DC voltmeter. So AC voltmeter is not as sensitive as DC voltmeter because AC signal will give 45% only of the full scale. AC voltmeter using halfway rectification is only approximately 45% as sensitive as a DC voltmeter. Multiplier resistor will be only 45% of the value of the multiplier resistor for a 10 VDC. Okay, so the sensitivity, the RS, and the voltage for AC signal will be 45% only, rather than 100% of DC signal. Okay, so average voltage, okay, that is read by the PMMC is equal to 0.45 Vrms. Okay, let's say Vrms is equal to 10, but the DC, but the meter, the PMMC meter will only read 4.5. Okay, this is the formula for RS. RS is equal to, we know that RS is equal to R total minus RM, right? R total is equal to V over I. Okay, so this is DC divided with I total or I FSD. Okay, so VDC is equal to 0.45 of Vrms. Okay, and AC sensitivity for AC meter is equal to 0.45 of SDC. Class, any question? Can I understand or confused? Can I understand or not?
Betul, saya ada soalan. Untuk bukti voltmeter with range tu memang fix 10 volt ke?
No. It is only example.
Okay.
Class, have you had your lunch? Makan belum?
Already.
Dah.
Esok dah puasa.
Sedang.
Esok puasa kan? Saya tak makan lagi. Tu saya sambil makan. Saya sambil makan buah kan. Kenapa? Okay. So this is only an example. Okay class, now example. Again, the example is 10 VRMS. Calculate the value of the multiplier resistor, meaning that RS, for a 10 volt VRMS range on the voltmeter shown in figure 4.19. Okay, so this is voltmeter. This is the whole circuit is voltmeter. Okay, so the range of the voltmeter is 10 VRMS. Okay, meaning that this is AC voltmeter. This AC voltmeter, okay, is based on PMMC. Okay, based on PMMC construction. This is PMMC. Okay. We remember in previous chapter to design or to convert a PMMC construction into a voltmeter, we add series resistor, right? Or multiplier resistor. Series to the PMMC. But to read AC signal, we should add a diode. So this circuit will become AC voltmeter with half-wave rectifier. Okay. So now we should find RS, the value of RS. There are a few methods. Okay. But the final answer must be the same. Okay. How to find RS? Okay, we know that RS is equal to R total minus Rm. Okay, RS is equal to R total minus Rm here. Okay, let's go to this method. Okay, so this will become method 3. Okay, so R total, we know that R total is equal to S multiplied with V range. Okay, so if you use AC for S, the V range must be AC as well. If you use DC for S, so the V range will be DC as well. Okay, and the minus Rm. So this method use AC value. This method use DC value. Okay. So SAC, we know that SAC is equal to 0.45 SDC. Okay, because sensitivity for AC signal will be 45% of sensitivity for DC signal. Okay, and then multiply with V range AC. VAC, so it is given 10 V, 10, okay, so 10 VRMS is equal to AC signal. Multiply with 10 minus Rm is given 200. So SDC is equal to 1 over I FSD, okay, or I total of the circuit. Here I total is equal to 1 milli. Okay, and then we get 4.3 kilo ohm. How about this formula, this method? Okay, RS is equal to S DC multiply with V range, but V range here is in DC as well. minus Rm. Okay, so SDC is equal to 1 over 1 milli. 1K ohm per volt here is equal to 1 over 1 milli. We get 1K. Okay, so SDC here, this is SDC. SDC here. Okay, multiply with V range. Okay, 10 V here is AC, so we cannot directly use this 10 volt. We should convert this AC to DC. How to convert VAC to VDC for half-wave rectification? Okay, so VDC is equal to 0.45 V RMS. Here, 0.45 multiplied with V RMS. V average. V average is the volt is same as VDC. Same as VDC. Okay. V average is same as VDC. Okay. And then minus Rm. So 1K multiplied with 0.45 multiplied with VRMS is equal to 10. Okay, and then minus 200 ohm. Okay. So finally we get 4.3 kilo ohm. How about this formula? RS is equal to, okay, RS is equal to this formula 0.45 VRMS or VAC divided with I, okay, I total or IFSD minus RM. So this formula is obtained from this, okay, 0.45 multiplied with the AC signal of voltage 10. Okay, divided with 1 milli and we get the same answer. Any question? Any question? Can you understand? Okay.
I have a question. Hello.
Any question?
Yeah, I have. The rate square is the equation given, or that is the third method. Method 1, method 2, then the right hand side.
Yeah.
Is third method.
Yeah.
Oh, okay. Thank you, madam.
Okay. Okay, if you understand half-wave rectifier, so full-wave rectifier is the same concept, but we just double the value. Okay, so this is AC signal comes from TMV supply. It is more desirable to use a full-wave rectifier than half-wave rectifier in AC voltmeter because of the higher sensitivity rating. Okay, so this is AC signal. And then we add full-wave rectifier circuit. In full-wave rectifier, we have 4 diodes. Have you learned about full-wave and half-wave rectifier? I think you have learned in principle of electric and electronic subject, right?
Yes.
Yeah.
So for this is the output for full-wave rectifier circuit. The negative signal will be, so during the negative half cycle, there is signal. So this is the output of the full rectifier circuit. So again, VRMS is equal to VP over cert2, VDC is equal to V average or equal to V output. So it is equal to, okay, we multiply this with 2. So 2 multiply with VP divided with 5. Okay. So it is equal to 0.636 VM. VM is equal to VP as well. Okay. So you should remember this formula, or you can just refer to your notes. VRMS is equal to VP over cert2. VDC or V average is equal to VP over pi. Okay, but for full wave rectifier, you must multiply with 2. Okay, so finally V average for full wave rectifier is equal to 0.636 VM or V peak. Okay. So, V peak is here, or I peak. Okay, so here the signal is current. Okay, I. So this is peak value or I peak. This is RMS value. It is about 1 over cert2 is equal to 1 over cert2 is equal to 71%. Okay, VRMS is or IRMS is equal to 71% of peak value, and average value is lower. It is 1.636 of VM or IM here. Okay. Bridge type rectifier is most frequently used for full rectification. This is bridge type. Okay, so D2 and D3 conduct in positive half cycle. During the positive half cycle, okay, during the positive half cycle, meaning that for positive signal, okay, this is during the positive half cycle, this is during the negative half cycle. During the positive half cycle, the signal is positive. During the negative half cycle, the signal is negative direction. Okay. So during the positive half cycle, D2 and D3 conduct. Okay, so current will flow through this is positive half cycle. Current flows through D2 and then go to RS, go to the PMMC, and then go to D3 and back to supply. Okay. And then during the negative half cycle, D1 and D4. Okay, so for negative half cycle, the current will flows like this. Okay, from the negative supply, D4, RS to PMMC, and then go to D1 back to the supply. Okay, D1 and D3 cannot be conducted on the same time, of course. Okay, so this is full wave bridge rectifier used in AC voltmeter circuit. This is PMMC. Okay, we add rectifier, full rectifier to read AC signal. Okay, this is the derivation for average, V average or V out. It is equal to 0.636 of V peak. Okay. 0.636 of V peak. Okay. So 0.636 of V peak. V peak is equal to V RMS, cert2 V RMS. Okay. So this one multiply with cert2, we get 0.9 V RMS. So for AC meter circuit with full wave rectifier, V average or VDC or V out is equal to 0.9 V RMS. Okay, or it is double of half wave rectifier. In half wave rectifier, V average or VDC or V out is equal to 0.7. For half,
0.45.
yes, 0.45. So for full rectifier, it double 0.9 V RMS. So let's say DC voltmeter with PMMC voltmeter, okay, with V range is equal to 10 volts. So this is an example, okay, with V range is equal to 10 volt. Okay, imagine that this is DC voltmeter with voltage range, the full scale range of the meter is equal to 10 volt. When full wave rectification is used, the pointer will deflect to 90% of full scale. Okay, it is better than half wave. Okay, because for half wave, the pointer will deflect to what? How many percent?
45%.
Yes, good. 45%. So for full wave, it double. For example, the signal is AC 10 V RMS or 10 VAC. It is equivalent to 9 volt DC. Okay. This means an AC voltmeter using full rectification has sensitivity equal to 90% of the DC sensitivity, or it twice the sensitivity of half wave rectification. The multiplier resistor would be 90% as well of the value of the multiplier resistor for a 10 VDC voltmeter. Okay, so the formula for full wave is the same as half wave. You just change this 0.45 to 0.9 here. Okay, same goes for sensitivity. SAC is equal to 0.9 SDC. Okay, this is the summary of the formula for half wave and full rectifier for AC meter. Okay, SDC is equal to 1 over I. Okay, for half wave and full wave. SAC is equal to 0.45 of SDC for half wave. Okay, 0.9 SDC for full wave. Or you can calculate as S is equal to R over V range. Okay, R total here, R total here. Okay, divided with VAC because SAC. Okay, so AC here, AC here as well. How about RS? RS is equal to R total minus RM. Okay, RS can be calculated as S. So R total is equal to S multiply with V range. If you use AC, so SAC, VAC as well. If you use SDC, so VDC. Okay. Or 0.45 V RMS divided with I total. So this is AC, RMS is AC. Or here for full wave 0.9 V RMS. Okay. The meter scale is usually calibrated to give the RMS value of an alternating sine wave input. Practical rectifier. Okay. We skip example on AC. Okay, we learn on characteristic of practical diode. Okay, practical diode. Later we will combine calculation on full rectifier and this calculation. Okay, it is about practical rectifier. Okay, so practical rectifier are non-linear devices, meaning that practical diode. Okay, this is okay. This one you have learned in last semester, right? For subject principle of electric and electronic. Practical diode are nonlinear devices. Okay, particularly at low values of forward current. This is forward current. This is reverse current. This is forward voltage. This is reverse voltage. At low values of forward current, meaning that at low value here, this is low value. So, meaning that this part, okay, or this part, it is non-linear region, non-linear. Okay, after on voltage of the diode, the current will become linear. This is linear region. This is non-linear region. Okay, same for this. This is diode characteristic. Okay. Hence, the meter scale is non-linear as well. In this part, the meter has low sensitivity because of high forward resistance of the diode. Also, the diode resistance depends on the temperature. Hence, okay, this is the point to be mentioned. Shunt resistance is added to improve the linearity. Okay. So we add arc shunt. Okay, this is for half wave rectifier. This is for full wave rectifier. We add arc shunt to improve linearity. Okay. The meter movement is shunted by a resistor arc shunt. Okay, this is arc shunt. We add arc shunt in order to draw more current through the diode D1 and move the operating point into the linear portion of the characteristic curve. Okay, when we add arc shunt with Rm, the equivalent resistance here will become lower or higher. Lower, okay? Because of parallel circuit, right? Parallel resistance. So when the equivalent R here becomes lower, current becomes higher, right? So that's why to move the operating, okay, in order to draw more current in through the diode D1, more current here, and move the operating point into the linear portion, okay? When the current becomes higher, we can move to the linear portion. Okay, this is a low current. Okay, here, non-linear region. Okay, when current becomes higher, it is in linear region. In the negative half cycle, diode D2 conducts. Okay, so just now for positive half cycle. During the negative half cycle, D2 is conduct and the current through the measuring circuit, which is in an opposite direction, bypass the meter movement. Okay, now we go to the calculation for this is full wave, this is half wave. Okay, design a voltmeter for a 10 V RMS AC range on the circuit shown in figure A and B. Determine the AC sensitivity of both design. So, this question did not specify what parameter should you find instead of AC sensitivity. Okay, design a voltmeter. So, what to find? RS, okay? RS, because IFSD is given, RM is given, V in is given. We just ignore D1, D2 here. So you should find RS. So design a voltmeter here means to find RS. Okay, for figure A is half wave rectifier circuit. Okay, so RS is equal to if you use this formula, so just substitute Vrms is equal to 10 as stated in the equation. Okay, and you will get 4.4 kilo ohm. And then you should find AC sensitivity as well. SAC is equal to 0.45 SDC, and we know that SDC is equal to 1 over current. Okay, 1 over 1 milli. So we get 450 ohm per volt. Okay, this is for figure B. Rs is equal to this formula. We substitute Vrms is equal to 10, and then IFSC is equal to 1 milli, and we get 8.9 K. SAC is equal to 0.9 SAC because of full wave rectifier, and we get this. Any question? Any question? Can understand? Can understand?
Can.
Shawal? Can you understand, Shawal?
Ya, doktor.
Faham tak?
Faham.
Okay, Shawal, what is different between figure A and figure B?
Full rectifier and half rectifier.
Okay, good. Meaning that you are with me. Okay, paying attention to my class. Okay, seems like this is an improvement added to the half-wave rectifier circuit where we add shunt, resistor, and diode. To what? Why we add R shunt and diode?
To improve the linearity.
Pandai. To improve linearity. Okay. In the half-wave rectifier shown in figure, diodes D1 and D2 have an average forward resistance of 50 ohm. Okay, 50 ohm for D1, 50 ohm for D2. Okay, 50 ohm is the average forward resistance of diode. Okay, and I assume to have an infinite resistance in the reverse direction. This is for forward resistance. Calculate RS. Where RS? RS is here. AC sensitivity and DC sensitivity of this voltmeter. Okay. So I paste the figure here. Find RS. Okay. RS is here. How to find RS? Okay, we know that R total for this circuit is RS plus RD, RD1 plus this equivalent R for parallel path. How about D2? How about RD2? No RD2 here. How about RD2?
Short circuit.
Short circuit.
Tak ada sebab positif.
During the positive half cycle, D2 is off. D2 is open circuit. Okay, open circuit. No conduction for D2. Okay, so RS is equal to R total minus the rest of R. So how to find? So we don't know R total. We have to find R total first. R total is equal to, we know that R total is equal to VDC over I total. This is half-wave rectifier circuit. So R total is equal to 0.45 Vrms over I total. Okay, VDC or V average for half-wave rectifier is equal to 0.45 Vrms. Okay, so we know Vrms. How about I total? I total here is not 100 microamp only. Okay, we should find our I total. Okay, since RM is 200, R shunt is 200, FSD or IM is equal to 100 micro. So for sure, our I shunt here is equal to 100 microamps. So current here is equal to 200 microamps. Okay, so this one is open circuit. Okay, this part is open circuit. So we know that I total is equal to 200 microamps. R total is equal to 0.45 multiply with 10, we get 4.5. Okay, I recommend to exclude V and M here, so that you will not confuse. Okay, maybe you think that V is equal to a parameter or unknown. Okay, so 4.5 divided with 200 micro, you get 22.5 K. And we can find RS. RS is equal to 22.5 K minus RD is equal to 50 as given in the equation. And then minus 100. Why 100?
Parallel equivalent yang tu.
Okay, 200 ohm parallel with 200, we will get half. Okay, this is the final answer, RS. And then the next is to find SAC and SDC. SAC can be found by using this formula. Okay, R total divided with V range in AC because this is AC. So 22.5 K divided with 10 volts. Okay, you will get this. Or you may find SDC first because SDC is equal to 1 over I total, 1 over 200 micro. We get this. So SAC is 0.45 of SDC. You will get the same. Any question? Any question? Our midterm test will cover chapter 2, 3, 2 and 3 only. I think so. Okay, not including chapter 1. So please understand chapter 2, chapter 3.
Doktor, kalau RM dengan RS tu tak sama, nak buat macam mana kau memang dia akan sama?
Not necessarily it will be the same. So you just parallel, make it parallel.
Lepas tu kalau tak sama, mesti I dia pun lain kan? Nak cari I tu macam mana pula?
Nak cari I. So how to find I total? Ada tak example for the time being, Arshan is the same as RM. Okay, maybe Arshan is equal to RM. So, so what do you think? It might be a reason why RM is equal to Arshan. If RM is different with Arshan, definitely I will teach you how to get I total, right? Don't worry. So the example that we have shows that RM is equal to Arshan. Might be a reason. Okay, kat mana tadi? Okay. So the next example, each diode in the full rectifier circuit in figure has an average forward resistance of 50 ohm. Okay, so each diode here has 50 ohm and is assumed to have a infinite resistance in the reverse direction. Calculate RS, SDC and SAC. Okay, you know that during the positive half cycle, two diodes will conduct. Okay. So one here and another one is here. And then we have RS and then Rshan and RM. Okay. So we have to find RS. RS is equal to R total minus all R in the circuit. Okay, so R total is equal to RS plus 2RD. Okay, RD2 and RD3. And then plus Rshan parallel with RM. Okay, so again we have to find R total. R total is equal to R is equal to V over I. Remember that this is VDC. VDC for full rectifier is equal to 0.9 VRMS. Okay, so we know VRMS. We have to find R total. Okay, So 500 here, 500 here, 1 milli here. So of course, 1 milli also flows through our shunt. So currents flow through here is 2 milli. Okay, 1 milli plus 1 milli, we get 2 milli. 2 milli will flows through RS as well as I total. Okay. Okay. So R total is equal to 0.9 multiplied with 10, we get 9. Okay, 9 divided with 2 milli, we get this. And then RS is equal to R total 4.5K minus, okay, 50 and 50, right? 50 here, 50 here. Okay, minus 50, and then minus this R shunt parallel with RM 250. We get this. Any question? Any question? No? Okay, the next is to find SDC and SAC. Let's start with SDC. SDC is equal to 1 over I total. 1 over 2 milli, we get 500. So SAC is equal to 0.9 SDC. Okay, 0.9 of 500, it is 5450 ohm per volt. That's all. Any question? Any question? Okay, actually the rest you can read by yourself. Okay, because starting this subtopic until the end, it is the theory on other AC movement meter. Okay, other than PMMC. We have 5, right? So this is for other AC meter, electrodynamometer, and so on. Okay, so actually the master topic in this chapter is done. Okay, we have learned all about calculation in chapter 3. Next lecture will be tutorial on tutorial 3, tutorial on chapter 3. Any question? Can I understand chapter 3? I think very easy. But in tutorial 3, it is okay. The example in lecture is basic calculation. Okay. Question in tutorial 3 is more challenging. Okay, because we apply DC. We apply AC meter that we learn today. So we apply it for real application, meaning that we use AC meter that we have designed today to measure. Okay, to measure what? To measure voltage. Okay. So in tutorial 3 we have circuit, and then we use AC meter that we learned today to measure voltage in the circuit. Meaning that we combine circuit with AC meter. Any question? How many of you today? $45. Okay, no question? No question, okay? If there is no question, we can end our class today and I can have my lunch.
Doktor esok cuti
Lah.
Oh ya.
Our lab on Thursday kan?
Yang situ.
Public holiday kan?
Ya.
Betul.
So during this Thursday, no class because of public holiday. And okay, so you have to complete your report this week. Okay, so that next week, next week kan? Next week we will have class. Okay, supposedly no class on next week, right? But next week we will have class. You can continue your experiment, and we will have Q&A session or evaluation or assessment. Okay. Supposedly no class on next week, no class. Okay, but this week we have public holiday on Thursday, so next week we have class on Thursday for lab. Okay, okay tak? Okay tak macam tu?
Okay juga.
Okay, so we change next week to this week, this week to next week. Okay, so this week you holiday on Thursday, so next week we have class on Thursday. Okay, class, that's all for today.